So in this video, we'll talk about extending the previous examples and the limitations they had and how to deal with them. We won't work out the entire thing, primarily because this model requires an antiderivative technique that we haven't covered. So we don't have to work out the whole thing. The examples we did are sufficient. But I do want to talk about this other model. So there's something called the logistic growth model, and it basically incorporates the benefits are the pros of the other two models without the drawbacks. So the first model, the exponential model, assumed like this uninhibited exponential growth forever, which is just not realistic. That's not going to happen. The other model assumed that, well, we have this maximum, which I'll draw out an asymptote here real quick. And the model assumed that, oh, you're going to have growth like this, where you exponentially grow towards the asymptote. So you have this maximum you never quite reach, but initially you have this really fast growth period, and then you taper off at the end. But this also assumes that if you start out with nothing, that you have a faster growth period at the beginning. Like it grows even more quickly at the beginning, right? Which doesn't make a whole lot of sense necessarily. I mean, maybe it depends on the context. What are you talking about? But in general, it doesn't. So what would be a model that both has slower growth at the beginning and then also has this asymptote? What would do that? Okay, so let's say that the growth is somehow 5% of something, right? So 5% of 1 minus r over, say, 200, that's the number we had for the maximum. That would incorporate, that there's a maximum. That gives you the asymptote. But we also want the horizontal to be an asymptote, so that instead of jumping up like this at the beginning, it curves upward at the beginning. See how this growth here is more shallow at the beginning? And that's going to happen with causing the horizontal axis to be an asymptote. So if I say, let's multiply by r, so that when r is 0, when the current revenue is 0, the growth is 0. So if you've got no sales, you're kind of stuck there, which is not entirely realistic, but you'll see what I mean in a second. With the graph will make a little bit more sense. So what this assumes is if the revenue is currently 0, the growth will be 0, because when you plug 0 into this function, you get 0 growth. So 0 growth at 0 revenue. But it also assumes that when the revenue is 200, well, this factor will be 0. It will be 1 minus 1, which is 0. So you get 0 growth at your maximum as well. So the graph ends up looking like this. You have slow growth at the beginning. You have some quicker growth in the middle, and then the growth kind of tapers off at the end. That's not the best graph, but you get the idea. So this assumes slow growth at the beginning, intermediate to fast growth at the middle, and then tapering off growth at the end. Okay, this is much more realistic for a number of applications. I would imagine. Okay, so in say biology, if you track, say, the spread of an illness, as an example we can all relate to now, this is the model that tracks that. That's how it behaves. If you look at, say, the growth of a small business, that could. I'm not sure that the beginning is necessarily the most accurate. If you go take an advanced economics course, I'm sure they'll talk about which models best reflect, say, a small business, for example. But this kind of thing, the concept here is that you can build a model, a differential equation that models what you're describing, and the different factors, the 5%, the fact that you have a maximum, the fact that 0 revenue should result in 0 growth, that you can build in these different elements. You could say that my minimum is not 0. You could say, well, you know what? I don't want 0 revenue to be 0 growth. I want, if my revenue falls below a certain minimum, like what if my revenue falls below 1,000 per year? Well, then I'm just going to close up shop. There's no way to run the business. So you could do a different factor to incorporate that. And whatever factors you want to describe the different elements of what you think is going to happen, and you can solve that differential equation. You can get whatever model, and the graph will be whatever the graph is. It depends, right? But the idea is you can set up a differential equation that describes a real-world problem, solve the differential equation, and you get a function that describes the phenomenon without having to build the function piece by, just sort of by fiat, oh, I know what the function is, you can build the equation and then find out what the function is. So it's a really powerful tool. Anyway, this is the last video in this short series. Just to wrap up, we did a few examples of just straightforward how do you solve a differential equation. Then we did a couple of application problems, and I just wanted to sort of extend the concept and say you really could do lots of different things with this concept.